AC impedance spectrum, and we come to know that in ionically blocking electrode, we have a ionically blocking electrode. You're going to have a electrical circuit like Berkeley resistance and the double layer capacitance, and in parallel we're going to have a geometric capacitance like this. And then we know we're going to have R and B and G, and omega, we will see G R B equal to 1, and in this case we're going to have omega C I R B equal to 1. Okay. And we just approach this to have this an intuitive approach. All right. Today we're going to make a mathematical approach to verify the results. Okay. Mathematical approach. Now let's think that we have two things in parallel like this, and then first we want to get y1 first. Okay, z1 is lb plus jx, and x is going to be omega c. Okay, y1 star is nothing but j1, 1 over j1 star, so it's going to be rb square plus x square jx rb square plus x square. Then the y total is y1 star plus y2 star, and rb over So this is the mathematical approach. Then we have the same conclusion that they had following the intuitive approach, right? Today we are going to discuss about the more realistic case where we have M, Mx, and Mxy, the mixed conductor case. Now in this case, we are going to have Rb, and in the double layer capacitance, it's going to be parallel connected with the Warburg impedance. And then again, the whole thing is we have geometric capacitance like this. Here the W is called Warburg impedance. And this is diffusional impedance. And of course it is related to the phenomenon that lithium ion and with electrons combination you form a lithium atoms, and then it diffuses inside the cathode with the chemical diffusion coefficient, chemical diffusion coefficient. So the Warburg impedance is something related at this reaction surface. Okay. This is the case where we are during the discharging reaction, but in a charging process, something can be said. Okay, the ionization of lithium, and the phenomenon is just the other way around, the opposite direction, but the chemical reaction is the same. Of course, the charging process and discharging process does not have the same rate. The rate should be different. Okay, even though chemically it is the same phenomenon, but the rate should not be the same. Now we can arrange the general form of impedance. General form of impedance, G star A minus alpha J B this is the general form of impedance. Okay, in here A and B and alpha is not a function of frequencies. So in case of a resistor, which is going to be symbolized like this, the alpha is equal to 0, A is equal to R, and B is equal to 0, so that GR star is going to be R. In the case of a capacitor, the alpha is equal to 1, A is equal to 0, and B is equal to 1 over C in the general form. Okay, so the star now impedance is going to be minus J 1 over omega capacitors, like this. Now, for the Warburg impedance, it's a symbol as W, something like this. In this case, alpha is 1/2, and A equal to B, and that is proportional to diffusion coefficient, so that Warburg impedance now is A omega minus 1/2 minus J A omega minus 1/2. So if you look into this Warburg impedance, you can immediately see that the A is equal to, here this is R part and this is the X part, right? So if you plot in minus X or R, just the Warburg impedance just says you are going to have a straight line, something like this. And then the slope is going to be 45 degrees, something like this. And the position is going to be moving in this direction as diffusion coefficient goes down, because this A is proportional to the square root of D. Okay, 1 over square root of D. So, about Warburg impedance. Now the impedance, Warburg impedance, is going to be said as JA minus 1/2, like this. Okay? And then we want to relate this to the R plus JX stuff, okay? In order to do that, A omega minus 1/2 minus J omega 1/2 A omega. Okay. And then A omega minus 1/2 J okay. Now we know since impedance is going to be Rx plane, and that is J 1 over omega and 1 over C. Okay? So Warburg impedance capacitance here is corresponding to this value, which is A minus 1 omega minus 1/2, and that is A omega 1/2. So that is the capacitance characteristic of Warburg impedance. And constant A is proportional to the d to the minus 1/2, so that Warburg capacitance should be proportional to square root of d and 1 over square root omega. Now, if you look into this capacitance should be is related to the dielectric constant in area and in thickness, and then among these, only the d is the variable. So in a Warburg d, the d should be related to the neutral lithium and electron combination lithium plus. And this d is some process related to the chemical diffusion happening at x equal to 0. Okay? We can have the capacitance characteristic, capacitance nature in this reaction, and the d is the only variable. So for this chemical reaction, we can think some thickness here, which is going to be modulated by the frequency that we apply for the measurement in AC spectrum. And that means this d is proportional to the chemical diffusion coefficient, and this d is related to the frequencies that we apply. Now, this is reasonable in a sense that if this lithium diffuses out with a diffusion coefficient here, and if the cathode material has a high diffusion coefficient material, then this d becomes narrow and narrow. So we have a high Warburg capacitance. That is reasonable to assume. Okay, and if you have a high frequencies, of course the d is going to be shortened, so that it is related to the Warburg capacitance that we measure. But the important thing is it does have a 45 degrees in minus x and r plot in any sense. Now we have to modify a little bit to make the circuit analogy more realistic. And then we put the capacitance, AA capacitance, and Warburg impedance. And before that, we are going to have some resistance theta called, this theta is called charge transfer transfer resistance. And if you look into this reactions, the charge is going to be transferred. In this case, lithium is going to be transferred to the atomic lithium. And if it is a discharge, the charging reactions, then it should be lithium is going to be transferred to the lithium plus. Okay? This is for the discharging process. And this is for the charging process in the barrier. Okay? So this kind of a charge transfer, in this charge transfer, electron is involved, and the movement of electron should be related to the resistance that you call. So people said CTR, charge transfer resistance, should be related to the whole process. And then Warburg impedance, which has nothing to do with the electron transfer, but really related to the capacitance nature for these reactions. Okay? And that is related to how fast the lithium is going to be diffused out from the surface, or how fast the lithium can diffuse towards the surface where the reactions are in a charging process. So this Warburg is related to the diffusion coefficient of the reactive element, but this charge transfer resistance is nothing to do with the electroactive species diffusion coefficient, diffusion phenomenon. It's nothing to do with the diffusion phenomenon. Okay, so this circuit now is modified into this to accommodate the electron transfer and chemical diffusion process. So this is the final circuit analogy in a mixed conductor case, in the most cases that we have. And of course here the Warburg impedance is going to be represented as Z star Warburg impedance now is going to be omega minus 1/2 minus A J omega minus 1/2. Now, with this, we are going to do the intuitive approach first, okay? Intuitive. Intuitive approach. We know ZW is much greater than the CI and then much greater than the CG. Okay, that is the fact. So, number one, we start out with the very low frequencies. When we applied very low frequencies to this system, almost a DC characteristic at low frequencies, the circuit can be simplified as RB and theta. The capacitance terms is just infinity. And then Warburg impedance. And here, Warburg impedance consists of two terms. It consists of RL, okay, and then Warburg capacitance. And here the overcapacitance is going to be infinity again. So we are going to use the RL only, where the RL is the, it's going to be called, I should have a name for it. The limiting low frequency resistance of a wobble. The limiting or just DC nature of the Warburg. And then it can be in the minus X and R plot at the very low frequency. We start out with low frequencies, then go down like this, and then this resistance is going to be RB plus theta plus RL. Now, if we increase the frequencies further, as frequency increase, then the Warburg is going to be shorted. So we have RB here, and then theta, and then CI. Wait a minute.